Okay, let me experiment with a quick video doing an LU decomposition. One step at a time, and then efficiently and quickly recursively. So here's a matrix with some numbers. I'd like to do an LU decomposition. I understand it's based on elementary row operations. So I want to eliminate the 8 and 1. Negative 4 times the first row plus the second. Negative 1/2 times the first row plus the third. This is the elementary matrix that accomplishes that. And this is the result of multiplying those two matrices. So I get 2, 7, 1, and then 0, minus 26, and 4. And then 0, negative 7/2, 16/2 is 9/2, and negative 1/2 and 4/2 is 3/2. Now I'm going to do elementary row operations to remove this 9/2. Don't be afraid of fractions. All I have to do is multiply this number by this number divided by that number. So I will take 9/52 times this. That'll create minus 9/2. And I'll add it to here, and I'll put a 0 there. This is the elementary matrix that does that. So when I multiply this elementary matrix times this one, I will take 9/52 times this, which is negative 9/2, add it to this and create 0. 9/52 times 4 will leave me 18/26 after I reduce a 2. This is 39/26. 18 and 39 is 57/26. So we've come to this matrix. This is an upper triangular matrix. It was achieved with two matrices with elementary row operations. There's a single elementary row operation, two elementary row operations working from the first row. So now I understand that to get the LU decomposition, these are lower triangular. These are easy to invert and easy to multiply. So I will multiply by E2 inverse, and then multiply by E1 inverse, and then I'll have A is L times U. The L right here is going to be E2 inverse and E1 inverse, peeled off in the particular order. First I apply E2 inverse, and then to the left of that I apply E1 inverse. But what I appreciate is that E1 is easy to invert. The minus 4 and the minus 1/2 just become 4 and 1/2. E2 is easy to invert. The minus 9/52s becomes, or the 9/52s becomes minus 9/52s. And the product of those two in that order just because becomes the combination of those two inverse matrices. So now I have an LU decomposition. This is exploring every step with elementary matrices. Now let's do that quickly with a recursive operation. So the first thing I notice in my LU decomposition is that 8 divided by 2 appears in the first column, and 1 divided by 2 appears in the first column. In fact, in the LU decomposition, I must have this first column, and I must have this first row to produce this matrix. The next thing I notice is that if I perform the operations that are indicated by this, minus 4 times first row plus second, minus 1/2 times first row plus third, essentially thinking of subtracting the 4 and subtracting the 1/2 of the first row onto the second and the third, that I produce these numbers right here. I produce a 2 by 2 matrix. that I now want to do an LU decomposition on. How do you do LU decomposition on a 2 by 2 matrix? You must use this first column and you must use this first row in black. And when we do that, I take this number divided by minus 26, and this is the number I place here to do the elementary row operation. This is the inverse of the elementary row operation I'm going to do. The elementary row operation I'm going to do here is 9 over 52 times this will give me negative 9/2, which will eliminate this. The opposite of that is minus 9 over 52. That's what happens after I take this matrix over to the other side to invert. I've just already taken this matrix to the other side. So now I do 9 over 52 times this plus this is 0, and 9 over 52 times this, it's 36 over 52, 18 over 26. This multiply 13 top and bottom is 39 over 26. 18 over 36 plus 39 over 26 is 57 over 26. Now you see in these two quick recursive steps that we've done the same thing that we did with the elementary matrices here. I was just speaking and writing the elementary matrices as I go. Added benefit of this calculation is that I immediately see the determinant of the original matrix I started with, because this determinant is 1, and this determinant, canceling out the 26, is negative 57 times 2, which is negative 114. And you can take this and do determinant in the traditional way. 2 times 4 minus 64, minus 7 times 16 minus 8, plus 1 times 64 minus 2. Maybe I should write that lower so it's on the screen. Minus 120, minus 56, plus 62. If you work these out, this is a positive 6. Added to negative 120 is minus 114. So by all means, if you have to do LU decomposition, work efficiently with elementary matrices. You can write and track them like this. But you can do LU decomposition very efficiently and recursively by saying, what must be the first column? What must be the first row? Performing the operations that get you there, and then looking at the smaller matrix and saying, what must be the first column? What must be the first row? And then performing the elementary matrices that land you here. Practice that recursive definition on some LU decompositions.